In our lecture on May 18th, we have shown the process emulation of FinFET, but it was not completed, stopped just before epitaxial source strain growth. So today we will do that job. So let me just review our previous achievement. So first of all, color code has changed a little bit, but I think that this is not that major problem. Here you can see that sidewall. So sidewall, this is silicon oxycarbonitide, and it was deposited. So here we have the part for N MOSFET, and here we have a part for P MOSFET, and this is the starting point of our discussion. So today we will grow source and drain for P MOSFET, and let's just do it by a step-by-step manner. Previously, we just eliminate all the sidewall part, but in this time we will just eliminate the part for our P MOSFET. So let's just do it. So now for that purpose, I have introduced the mask for N MOSFET. So for N MOSFET part, it is preserved, protected, and only the part corresponding to the P MOSFET will be etched away. Okay, so now you can see that this N MOSFET is saved from etching, and still we have a P MOSFET where side walls are eliminated, and this is the remaining side wall. And yes, so now we have the case. Here fins are revealed, but actually this is not a silicon, but you can see that dummy-gate oxide is still found there. So actually we must eliminate this silicon dioxide for our future purpose. So let's just do it. So let's etch this silicon dioxide. And by performing this etching process, okay, now you can see that this silicon fin is now revealed. Of course, since N MOSFET part is still covered by this nitride, silicon oxynitride spacer, so we have only part for this P MOSFET. Okay, now we have the case for a P MOSFET, and now we have to grow the P MOSFET source and drain, but still we have the fin itself. Usually, in order to maximize the impact of silicon germanium source and drain, we intentionally etch this existing fin. So let's just do it. So it is etched. The fin is completely etched from top, and this is just silicon, and let's just eliminate it. So of course here we have other different dummy gates and fin, but they are all covered by different materials. And from the top view, only we can see is a silicon fin. So by performing this etching process, now we have the fin eliminated. Here we wanted to um, grow silicon germanium source and drain. And here, yes, so it is grown only on top of a silicon. Okay, it will take some time, but anyway, let's just do it together with me. So, yes, here we have this part is usually called as a cavity, source and drain cavity, and from this one, now we will have some growth of our silicon germanium material. Uh, let's just do it. So the basic mechanism to have this silicon germanium is explained. So during or waiting for its emulation. So let me just explain a little bit. So in this case, actually we have a silicon, silicon, silicon. So this bottom we have a silicon, and this two sides we have a silicon. In this case, if we send the silicon or silicon germanium atoms into it, and by the surface reaction between existing silicon crystal and silicon or germanium material, there will be the growth of this silicon germanium all the way on top of this silicon uh, crystal. Of course, even for other material, we may have a certain growth, but during this time, so we continuously eliminate this weak bond between other, other materials. So therefore, the remaining one is the one grown from crystalline silicon only. So what will be the growth of this silicon germanium? It really random. So whether it will grow, one atom will be attached to this part or that part or another part, we have no idea about what will happen actually to this case. So instead of taking any kind of deterministic simulation, which is already known from its starting point, uh, but instead we just make some random number generation to decide where we will have the grown silicon germanium atom. So that is typically called as kinetic lattice Monte Carlo method, because Monte Carlo, that is used for random number generation, the methodology to use random numbers. And kinetic lattice means that here we have a lattice structure of silicon, and there we just place a silicon or silicon germanium atoms on it. Oh, now it's done. So let me just have a look at the complete behavior. So all previous uh, reasons are shown here, but for better visibility, let me just eliminate that. Okay, now you can see that there is a certain amount of new layer, which is given as silicon germanium, and it is grown in this way. Okay, so from this cavity, they are grown, and eventually uh, from top and side they are merged, and eventually also the fin and another fin, uh, their contributions are merged here. Of course, if we reduce the growth of this one, then of course we can have different directions. But anyway, this is the typical behavior. And another one we wanted to say here is its a shape. So as you can see, this one, this the silicon germanium growth shows quite a typical behavior. I mean that here previously we had the fin and its shape just looks like a kind of a um, kind of a polygon here. Of course, their corners are rounded, but more or less their shape looks like this. Here we have a bottom and one segment, another segment, and another segment, and another segment. So it is known that shape of a silicon germanium layer grown by selective epitaxial growth just looks like a pentagon. So if we allow even further growth, then this rounded corner will be eventually become more sharper. But we have stopped here. Well, anyway, let's just come back to our problem. So now we have here PMOS source and drain, but uh, still we don't have no source and drain in this NMOS part because that was covered by this spacer. So now we must also have to do similar thing.